So, what is modular arithmetic? It is a clock. Well, kind of. So we can think of it as numbers wrapping around. So with a clock, after it hits 12 o'clock, it goes back to 1 o'clock, and then 2 o'clock, 3 o'clock. And this is, I would say, what you can say, same but different with modular arithmetic. Because modular arithmetic, instead of going from 1 to 12, it will go from 0 to 11. So if we have a 12, it will wrap back to 0. And now we'll be moving into a concept in modular arithmetic called congruence. So we'll be using the whiteboard now. So let's say that, let's just look at the formal definition of congruence. It says that for any three integers a, b, and m, a is said to be congruent to b modulo m if a minus b is divisible by m, which is a mouthful to say. But in short, what we mean is that let's get like three numbers. So a is equals to 5, b is equals to 3, and m is equals to 7. Wait, actually that's not a good example. A is equal to 5, b is equals to 2, and m equals to 3. And m here stands for our modulus, which is the number that we are working modulo of. Hence the word modular arithmetic. But let's say that we have 5 and 2. What's 5 minus 2? 3, yeah. And is 3 divisible by 3? Yes, it is. Which means that 5 is congruent to 2 modulo 3. So that is the proper definition. But there are much more intuitive ways to think of it. So let's begin with calculating a number modulo some modulus. So when we calculate a number modulo something, that is not a proper term in math. However, we can do it intuitively. So let's say we have a equals to 5 and n is equals to 3. What's 5 divided by 3 in terms of remainder? Like 1 remainder. 2. It's 1 remainder 2, right? So this means that 5 modulo 3 is equals to 2. Everyone following so far? And because 5 modulo 3 is equals to 2, we can say that 5 is congruent to 2 modulo 3. So this was the same way for 8, because 8 divided by 3 is 2 remainder 2. So 8 is congruent to 5 and is also congruent to 2. So I'll write the modulo. Modulo 3. Okay, anyone wants to give another number that is congruent to these three numbers, modulo 3? Any number, modulo. There's infinitely many. 11, yes, that's correct. 11 is congruent to 2 modulo 3. Because 11 divided by 3 is 11 divided by 3 is 3 remainder 2. Now, quick question. I'll use this whiteboard now. Is negative 1 congruent to 2 modulo 3? The answer is yes, because negative 1 divided by 3 is equals to negative 1 remainder 2. Because negative 1 times 3 is negative 1 times 3 is negative 3, and then negative 3 plus 2 is negative 1. And one more bit of intuition we can get is that, let's say we have 8 is congruent to 2 modulo 3, which we have already established is the case. If we want to find another number that is modulo 3, we can add 3. So 11 is congruent to 2 modulo 3. Because when we add the modulus, we are not changing the remainder, we are only changing the quotient. Everyone following so far? Alright. So now, when we have two numbers that are congruent, so let's say we have, again, let's just use 8 and 2 again. And we can say that 8 is equals to 2 plus k times 3, where k is some integer. Well, in this case, we know 8 and 2. So k will obviously be 2 by basic arithmetic. But basically, what this means is because we are finding our modulo by dividing and taking the remainder. So this number 2 is the quotient when we divide. So if we recall, 8 divided by 3 is equals to 2 remainder 2. Our 2 here is the k. Everyone following? Okay, so now I'm going to give you all a exercise, or rather a short question. Let's say we have 29 is congruent to 1 modulo 14. So 29 is equals to 1 plus k times 14. Find k. 2. Yeah, that's great. So it's 1 plus 2 times 14. And this form here, so the 29 is equals to 1 plus k times 14, is very useful when we want to perform some arithmetic calculations, which we'll be going into later. So this is a small illustration for congruence modulo 12. So you can see that 0 is congruent to 12, which is congruent to 24, and it's also congruent to negative 12. And negative 11 is congruent to 1, 13, so on and so forth. So now we'll be going through addition and subtraction, or specifically, addition holds modulo m. So let's say we have 2 integers that or should I say 4 integers, a, b, c, and d, and we have n, so 5 integers. A is congruent to b modulo n, and c is congruent to d modulo n. A plus c will be congruent to b plus d modulo n. It is always the case, no matter what a, b, c, and d are. So everyone following so far? So this means that we can do algebra with modulo n. And since, let's say c is a negative number, this also holds, because it holds for every integer. Then this means that subtraction also holds, so we don't need to do any extra work. It's just implied from addition. As for multiplication, it also holds. So let's go back to our a, b, c, and d. This time, a times c is congruent to b times d modulo m. Again, this is always the case. So, makes sense? Any questions so far? Alright, that's great. So, next slide. Now we're moving on to division. I'll be illustrating with an example this time because it's slightly more complicated. Let's have a, b, and c. So let's say that a, b is congruent to c. So as per the example of that, we have 3 times 5 is congruent, 3 times 4 is congruent to 5 modulo 7. And let's say we want to divide to get 3, but 3 is congruent to 1.25. I mean, that obviously doesn't make any sense, right? Because it's obviously not the case. And not only that, we cannot work with decimals in modular arithmetic. So that begs the question, what do we do to divide? It's like, we do something called finding a modular inverse. So a modular inverse is denoted by to the power of -1. So let's say that we have b, and then its modular inverse is denoted by b to the power of -1, like this. And by the laws of how modular arithmetic works, this b to the power of -1 must be 1 or congruent to 1 when you multiply it by b. Hence the name modular inverse. So this is the definition. And when we have a modular inverse, we can just divide by multiplying both sides by it. So let's say AB is congruent to C modulo M. A will be congruent to C times the modular inverse of B modulo M. Right, everyone following so far? Okay, nice. Next slide. So that begs us the question again. How do we find the modular inverse of B? Well, we can do it in Python really quickly. So David will now be going through it.
So as a quick demonstration, if you were to open like a Python shell, let's say our modulus is 10 and let's say b is 3. In order to find the inverse, one of the first few ways is that you can just try like 3 times 1, 3 times 2, 3 times 3 until you find one where 3 times number mod 10, in this case m is 1, right? So we can just kind of like we can just try this and then like just slowly like iterate 3, 4, 5, 6. But this is very long-winded and it's not really the ideal way. Python has a very handy function for us that is just called power inverse. So recall when Jaron said that to calculate our b inverse is basically b, we write as b to the power minus 1. You can do the same thing in Python where we call pow, which is the exponentiation function, but we are going to have 3 variables. So the first input is 3, which is our base. Then our second input is minus 1. We are basically doing 1 over 3. But instead of calculating 1 over 3 that we would normally do if you do this, we are going to add a third input parameter called 10, which is our modulus. So what this does is that it will calculate the inverse of 3, or like 1 over 3 mod 10. In this case, it is 7. And does anyone know why this is 7? Or like why it will be 7 such that 3 inverse is 7? Correct. 3 times 7 is 21, mod 10 is 1. So in this case, 7 is the number that is 3 inverse. So one question I'd like to ask is that since 7 is the inverse, right, is there any other number, not from 0 to 10, that's also a valid inverse? 14? Let's try that. Let's do 3 times 14 modulo 10. We see that it's actually not the case because 14 is 2 times 7. So when you do 3 times 14, we're doing 3 times 7 times 2, right? Because 7 times 2 is 14. So when we do this mod 10, we're actually doing 3 times 7 times 2 mod 10, of which, if you look at this, because 3 times 7 is going to be 1 mod 10, we are just doing 1 times 2, which will give us 2. In actuality, one of the other correct values would be 17, because 17 is 10 plus 7. So when we do 3 times 17 mod 10, we are doing 3 times 10 plus 7 in brackets mod 10. And then the 3 times 10 is going to get cancelled out by the modulus because it's already in the quotient. But 3 times 7 remains, which becomes 1. Any questions so far? Alright.
So here we have 3 times 10 plus 7. And if we expand it out, we get a 30. And because 30 is congruent to 0 mod 10, because 30 divided by 10 is 3 remainder 0, it just gets extracted away into a 0. And we can just ignore it and everything else is the same. So everyone following so far? Okay, then we'll be moving on to GCD. So, show of hands here, how many of you remember learning HCF and LCM in Sec 1? Yeah, so GCD is just a different name for HCF, or highest common factor, or in this case it's called greatest common divisor, which is the term that we use in cryptography a lot. So let's say that we have two numbers, 6 and 9, and we know that 6 is equals to 2 times 3 and 9 is equals to 3 times 3, where 2 and 3 are primes, right? So the largest number that divides both of them is 3. So the GCD of 6 and 9 is 3. Everyone following? So this is the concept of GCD. It is denoted by GCD bracket A comma B, or sometimes in math textbooks it's denoted by A comma B, but we will not be using this here because it's ambiguous. And now we'll be doing a quick exercise. What is the GCD of 12 and 20? Anyone? 4? Are you sure? Yeah, you're correct. So next one. What's the GCD of 19 and 2? 1. Yeah, that's correct. So it is 1. And when the GCD of two numbers are 1, we say that they are co-prime. Because as we recall, prime numbers are only divisible by 1 in itself. So this is in a way similar to primes, which is why we call them co-prime. And lastly, what's the GCD of 16 and 6? 2? Yeah, that's correct. Okay, so hopefully everyone has a good grasp on GCD now. Any questions so far? Alright, no questions. Okay, now we'll move on to the Euclidean algorithm. So, of course, when we have the GCD, or we have the concept of GCD, we will want to naturally ask, how do we find the GCD? And so, we have an algorithm called the Euclidean algorithm, which is able to find the GCD. And it is really quick, which is important for later. So, this was written this was written from another workshop, and I asked the person who wrote it for permission. But basically, the Euclidean algorithm works by starting with the two numbers. So let's say we want to have the GCD of 16 and 6. We first take 16 modulo 6, which is 4. So everyone sees why 16 modulo 6 is 4, right? Because 16 divided by 6 is 2 remainder 4. So now we have 4 and 6. Next slide. And after we have 4 and 6, we then take 6 modulo 4, which we get 2. And we go on. We take 4 modulo 2, and we get 0. So once we have one number that is 0, we will have one other number that is non-zero. And we will notice that this number here is the GCD of the two original numbers, which is how, or in essence, what we are trying to find. So now we'll be going through how the Euclidean algorithm is implemented in Python.
So there are like two ways in which you can implement GCD in Python. So the first, which is in the slides, is we define it ourselves. So for example, if we define the GCD of A and B, where A and B are two numbers, by the Euclidean algorithm, we're going to use a bit of a concept called recursion. So if B is 0, in which case we have the GCD, we return A. Otherwise, we are going to call GCD of B with A modulo B. So what this does is that every time it calls, it will call the GCD of a smaller value by using the Euclidean algorithm. So we slowly modulo it with the smaller number, and we repeat this process until eventually one of the numbers is 0. Once the number is 0, we just return the other number, which will be the GCD. So for example, if we do GCD of 16 and 6, we will see that this returns 2. And if we do like GCD of 15 and 35, if we do GCD of 15 and 35, it also returns like 5 in this case. So this is one way to compute GCD manually, and when you're doing GCD of like other variables that may not be integers, you may want to remember this general format, because it will be useful at some point later. That said, there are other ways of doing GCD. So the most simplest and direct way is just from math import GCD. Then you can just directly call GCD of let's say 14 and 2, and you get 2, for instance, or like 14 and like let's say 28 times 3, and you get 14. This is the more straightforward way. You just import it directly from the math library. Yeah.
Yep. So we can import GCD from the math library directly, which is what I would do, and I think everyone will do it because it's so much more convenient. But it's good to understand it. So now, if we go back to division, here's a question: what's the inverse of 3 modulo 6? I mean, naturally, because you need Python to calculate it, we're not going to make you calculate it. But David, can you calculate what 3 to the power of -1 modulo 6 is?
Sure, Jeron. I will calculate what 3 inverse 1 modulo 6 is. Let's try this out. And as you can see, we get a error from Python that says that the base is not invertible for the given modulus. But what does it mean? So the base is 3 and modulus is 6. So what this is saying is that it's not invertible, which I guess it could mean that the inverse doesn't exist. But of course, there's a question of like, why is it that in this scenario it doesn't exist when something like, let's say 5, for example, has a inverse, or like something like 4 doesn't have an inverse as well. So there are some questions as to why that is the case, which I believe we'll answer today.
Yeah. So does b to the power of -1 always exist? I mean, the answer is obviously no, because we just showed something doesn't exist. So let's go back to our definition of the inverse. So we have b to the power of -1, and since multiplication is commutative, which means that a times b is b times a, we can do b times b to the power of -1 or b to the power of -1 times b. And that is, by definition, congruent to 1 modulo m, for some modulus. And this means that we mentioned earlier, b to the power of -1 times b is equals to 1 plus k times m. And we'll do some algebraic manipulation here. Next one. We'll move the km to the left, so subtract both sides. Subtract km from both sides. b to the power of -1 times b minus k times m is equals to 1. And now let's let the GCD of b and m be x. So we go back to we remember what GCD is, and we know that x is the greatest number that divides both b and m. So it's by definition a factor of both. And so now move over to this whiteboard. We have b times b to the power of negative 1 minus k times m. And we notice that since x is a factor of both b and m, it is a factor of the whole expression because we can sort of factor out x. So let's say we have b, right? So b is equals to x times b over x. Make sense? Because we're just bringing out the x. And b over x is also an integer. So after that, we add on b to the power of negative 1 minus k times x times m over x. And we factor out x times whatever, it's not important. And so this whole expression has x as a factor. But we remember that this whole expression is 1. So since x is a factor of 1, what can x be? 1. Yeah, that's correct. X is 1, which means that the GCD of b and m must be 1. Otherwise, the inverse just does not exist. And so, if we go back to our earlier example with 3 and 6, we notice that the GCD of 3 and 6 is 3, and the GCD of 4 and 6 is 2. Whereas the GCD of 5 and 6 is 1. So, we can see that 5 is the only number among 3, 4, and 5 that have a base or has an inverse that exists. So this is what we need to keep in mind when we are doing division in modular arithmetic. So now, after we have gone through GCD, we would naturally go on to its brother, LCM, which is the lowest common multiple. So let's have two numbers a and b. So let's say a is equals to 6 and b is equals to 8. So a is equals to 2 times 3 and b is equals to 2 to the power of 3. So the lowest common multiple is the smallest number that is a multiple of both, which means that it is the smallest number with both a and b as a factor. So the LCM of a and b is 24. So we can verify. What's 24 divided by 3 divided by 6? 4. Yep. 24 divided by 8? 3. Yep. So there's no remainder or it's not a decimal. So they are multiples. And so this is in essence what LCM is, but we can go further. We can sort of establish a relationship between LCM and GCD. So we remember that LCM 6 and 8 is equals to 24. And 6 times 8 is equals to 48. And the GCD of 6 and 8. What's the GCD of 6 and 8? 2. Yeah. So we see that 6 times 8 over 2 is equals to 24. So our LCM is equals to the product of the two numbers divided by the GCD. And this is always the case. And this is how computers calculate the LCM. So now we'll be having another quick exercise. What's the LCM of 12 and 20?
64.
60. Yeah. Next slide. What is the LCM of 19 and 2? 38. Yeah. And what's the last one?
48.
Yeah, 48. Okay, so hopefully everyone has a good understanding of LCM now. Again, if you have any questions, feel free to ask. Okay, next slide. So now we'll be going through how to calculate LCM in Python.
Much like GCD, Python's math library also has the LCM function. So you just do from math import LCM. And to calculate the LCM of two numbers, we just call LCM. So for example, if you want to do LCM of 16 and 6, we can just do from math import LCM 16 6, which will give us 48. Then to verify, we do like 16 times 6 divided by the GCD of 16 and 6, for example. We see that we actually get a value that's 48.0. The 0.0 is because we are dividing it using 1 slash, which gives a float. Instead, if you want to make it integer, which we normally do, we apply 2 slashes to take the quotient, which is just 48 for this. Anyone have any questions about GCD and LCM? Okay.
My bad, I was drinking water. So now we'll be moving on to an identity called results identity. So results identity states that given two integers a and b, so let's define our integers. Let's just do a is equals to 5 and b is equals to 10, right? There exists two integers, x and y. So we know a and b, but we don't know x and y. But we know that there are integers such that ax plus by is equals to the GCD of a and b. So let's substitute in our a and b. We know that 5x plus 10y is equals to, what's the GCD of a and b? 5 and 10? 5? Yep. So 5x plus 10y is equals to 5. There are some integers here that fulfill this. I mean, for this equation, we obviously know x is -1 and 10 is, and y is 2 by eyeballing. But for larger numbers, this is less straightforward. But we have an algorithm called the extended Euclidean algorithm, or XGCD, which can find us these two integers. So now David will be demonstrating the extended Euclidean algorithm. What a mouthful.
So the extended Euclidean algorithm it builds upon GCD, but it returns our additional x and y values, whereby ax plus by is equals to the GCD. So you can copy this code here. I've also sent the code in the Discord as well on the Crypto General. But so if you were to kind of like define the function, it's just XGCD a and b, and then we'll also use a bit of recursion. So that's it. You don't have to understand why this algorithm works. Even for example, I don't particularly recall off the top of my head why it works. I just know that the algorithm exists and it works. So that's basically about it. So I'm just gonna apply the Euclidean algorithm here, and then once that's done, we will then do x equals to y1 minus b quotient a times x1, then y equals to x1, and then return g xy. So now, for example, if you do XGCD of 5 and 10, you'll see that we get 5, 1, 0, which makes sense because 1 times 5 plus 0 times 10 is going to be equal to 5. So then again, if you do something like 16 and 6, for example, we see that it returns the GCD, which is 2, and minus 1 and 3. And if we do the math, we see that minus 1 times 16 plus 3 times 6 is going to be equal to 2. And this works for really big numbers. So if I just do this and this as well, for instance, we see that it returns really large numbers. And this is a very effective algorithm for giving us this a and b, this x and y, when we can't directly see what the numbers are that will give their GCD. So in this case, if we have two numbers here and we're trying to find their x and y, such that this times this plus this number times b gives 1, we can use XGCD to recover this. There's a lot of very use cases for this, which Jerome will cover later. I won't give you all time to copy this. It's already in the Discord, and if you need to copy, you can copy it straight from there.
Yeah. So as David mentioned, this will be used for an attack later for RSA. So this is set attack. But now I want to draw your attention to the first application, which is finding modular inverses. So we recall our definition for the third time already. B times b to the power of -1 is congruent to 1 modulo m. So earlier we just used that Python function pow b -1 m to find it. But now we'll be exploring how it works. So again, we expand into b times b to the power of -1 equals 1 plus km, and then bring it over. So bring km over. So b times b to the power of -1 minus km is equals to 1, like this. And then since the GCD of b and m is equals to 1, so we recall our original results identity statement, where it says that for some integers a and c, ax plus cy is equals to GCD a and c. And here our c is our m, and our a is our b. So we're just substituting it in. Everyone following so far? So since the two have a GCD of 1, so this whole thing is just going to be 1. we can find x and y, which are in this case our k and our b to the power of -1, like this. And we can throw away our k, that's not important. But what we really want is our b to the power of -1. So again, this is how the power b -1 m works in Python.
So it's like a quick example. If we do like, recall earlier we did like 3, finding the inverse of 3 and modulo 10, right? If we were to run like XGCD of 3 and 10, we see that we actually get 1 minus 3 and 1. So we know that minus 3 times 3 plus 1 times 10 is 1. And in order to find the inverse, we know it's minus 3 modulo 10, because we're always working in mod 10, which in this case happens to be 7. So this is one way in which you can use XGCD to find the modular inverse of a number, allowing us to basically do division. So now because we know that 1/3 mod 10 is 7, but you want to divide any number by 3. So for example, let's say we have 6 and you want to divide this by 3 in mod 10, for example, you can just do 6 times 7 modulo 10, and we see that that's 2 because 6 is 2 times 3. So this is one way in which we use modular inverses as a way to do division and to use XGCD to recover them.
Yeah. And so now we'll be moving on to our 5th operation, which is exponentiation. So we remember in primary 2 or primary 1, we had the 4 operations of whole numbers. Now we have the 5th one, which is just repeated multiplication. And surprise, surprise, this holds as well modulo m. So we'll not be going through why it holds, but in short, on the slides there's a good explanation, but we'll just go through it. So moving on. So now this begs the question though. Let a and m be integers. What is a to the power of m congruent to modulo m? Is it 1? Is it 0? Anyone want to take a wild guess? Anyone want to take a wild guess? It's A. In sometimes, yes. So it actually depends on the nature of m, or more specifically, the prime factorization of m. So what you mentioned just now, a to the power of m is congruent to m. Yes, that's the case for some m. As for which m, we'll figure this out later. So now we'll bring you into a theorem called Fermat's little theorem, where let's define our variables again. So let p be any prime. So 7 is a prime, so we do p is equal to 7. And let a be like 2. Fermat's little theorem tells us that 2 to the power of 7 minus 1, or 6, is congruent to 1 modulo 7. So David, can you calculate 2 to the power of 6 modulo 7? It's 1. So with that in mind, let's change our variables again. Let's have p is equals to 11, a is equals to 6. What's 6 to the power of 11 congruent to, 6 to the power of 10 congruent to modulo 11? Anyone? Anyone? 1. Yep, that is correct. So this is David did type it out on the screen. But basically, if we go back to the slides, this theorem, so a to the power of p minus 1 is congruent to 1 modulo p. It's true for any prime and any a, except 0. But that's beyond the point. So everyone following so far? Any questions? Alright. So this begs the question for like the 5th time I've said this. What if p is not prime? So now we'll be going into another theorem called Euler's theorem. So if you guys know Euler from 2.768, it's the same guy. So let a and m be integers. So let's say a is equals to 6 and n is equals to 10. 6 to the power of 5 of n, this is the Greek letter phi, is congruent to 1 modulo n. But what in the world is phi? It is the Euler's totient function. So remember that we have fx is equals to x squared plus dot 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 or whatever. Those are functions. Similarly, we have Euler's totient phi x equals equal to something. But the something is a bit different from just a polynomial or x squared plus whatever whatever. Next slide. So now we'll be calculating Euler's torsion function. So we'll use the same number, which is 10. So n is equals to 10. We want to find phi of n. And we remember that n is equals to 2 times 5 because this is the prime factorization. So for each prime factor, we'll take each prime factor minus 1. So 2 is 2 minus 1. And for 5, what do we do? Remember for 2 we did 2 minus 1. For 5, what do we do? Minus 1? Yeah. 5 minus 1. And we get 1 times 4. So phi of n is 4. This is the case for n is 10. But now I'm going to bring in different n, where n is equals to 40. And what is the prime factorization of 40?
Two cube times 5.
2 cube times 5, yes. So n is equals to 2 cube times 5. And phi n is equals to, what do we do with the 5 first? Yeah, 5 minus 1. And now, what do we do with the first 2? So like we have 2 times 2 times 2 times 5. What do we do with the first one? Minus 1. 5 minus 1 times 2 minus 1 times, we have another times here. So over here, since we have a prime power, so it's like 2 to the power of 3 instead of 2 to the power of 1 like we had for 10. 3 people just cough in the same like 2 seconds. You can also please. We will take 2 to the power of 3 minus 1. And that is our Euler's torsion. So if we evaluate that, that's 4 times 1 times 4 is 16. So this is how we find our Euler's torsion for n equals 2 cubed times 5. And we remember that every single number is equals to some product of p to the power of something times q to the power of something, where q and p and q are primes. Okay, more of p times q times r times whatever primes to the power of something. And so we have derived a formula to, or not derived, we have found a formula to calculate the Euler's torsion for any n, any integer n. And so if we go back to our theorem, we see that we have a to the power of phi n equals to 1, is congruent to 1. So let's do n is equals to 20 and a is equals to 6. What's the phi or Euler's torsion of 20? Remember 20 is equals to 2 to the power of 2 times 5. 10. Okay, so let's do 4 minus 1 times 2 minus 1 times 2. Are you sure this is 10?
Oh.
5 minus 1.
5. Oh, 5 minus 1, my bad. But are you sure this is 10?
Yeah, it's not.
Yeah, you want to try it?
8.
Yeah, that's correct. So we remember we have a 5, then we minus 1, a 2, then we minus 1. And we have 2 squared, which we bring down to 2 to the power of 2 minus 1, which is 2 to the power of 1, which is 2. And this means 8. So Euler's theorem tells us that 6 to the power of 8 is congruent to 1 modulo 20. Is this the case? No. That is weird.
It needs to be co-prime.
Oh, my bad. Okay, so Euler's theorem only accounts for, can we go back to the slides? Euler's theorem only accounts for A where A is co-prime to n, which means that the GCD of A and n must be equals to 1. So over here, I did not account for that, and as you can see, it is not equals to, a to the power of totient modulo 20 is not equals to 1. So since n is 20, as long as any number is not a multiple of 2 or 5, it will be co-prime. So here David is going through all the odd numbers except 5 and 15, and we can see that they are all equals to 1. Everyone following so far? All good. Any questions? Okay, great. Because this is a very fundamental building block that we will be using a lot later. So it's important to get familiar and comfortable with this now. Yeah. So other than that, for Euler's theorem, we realize that phi of p for some prime, so let's say phi of 7, is just 7 minus 1. And if we go back to Fermat's little theorem, we see that a to the power of p minus 1 is congruent to 1. And so we see that Euler's theorem is really just a general case of Fermat's little theorem, where p is not prime. And if p is prime, they are the same theorem. So moving on. Now we'll be going through an exercise. Okay, we'll be playing a sort of game where whoever is the first one to answer the questions gets some snacks. But my hands are kind of wet, so I'm not gonna touch the snacks here. Okay, I'll you.
Yeah, sure, I'll get it.
Thanks. My hands are kind of sweaty.
Just a reminder, please do not eat in this meeting room. You can eat the snacks during lunch, but just don't eat it in this room. Thank you.
So, what's the Euler's solution of 13? 12? Yeah, that's correct.
Who said 12?
The one on the chair at the back.
Oh, you? Okay. I'll leave it there. Okay.
Okay, next question after he has taken that out. What's the Euler's solution of 15? Please give others a chance. Yeah. 8. Yeah, that is correct, because 15 is 3 times 5, and you minus 1 minus 1, you get 8. So, last question. What's the Euler's solution of 8? Anyone who has an answer? Wait, I heard someone? 4? Yeah, that's correct. So here we have 8 is a prime power, so it's to the power of 3. And we can get 2 minus 1, and after that we can get to the power of 3 minus 1, and that is just 4. So again, this is a really important concept, so I do encourage everyone to ask questions if you have any. Any questions? Alright, if no questions, then we'll move on. So back to exponentiation. If we have a and m, so let's say a is equals to 3 and m is equals to 7, which m is prime. A to the power of m is congruent to a times a to the power of m minus 1. And because we want to force in, because by intuition we will want to sort of manipulate the equation so that we get a number that is familiar, which because we have from Fermat's little theorem, we have a to the power of n minus 1 is congruent to 1 modulo n. So we want to try and get that, which we do because we can just take out one of the a's, because a to the power of n is congruent to a to the power of a times n minus 1 because of how exponents work. After that, we simplify. We do a times, what's a to the power of n minus 1 modulo n? 1. Yeah. A times 1, and that is just 8. So to answer our question from before we went into Fermat's little theorem, and you also mentioned, if n is prime, a to the power of n is congruent to 8. So that answers our question. Next slide. Now, we'll be going through how to implement exponentiation modulo n. But before that, let's take a look at the code on the right. Why is it that we can't do a to the power of b in Python and then modulo n? Anyone want to take a walk with us?
It's not co-prime.
No, it doesn't matter if it's co-prime or not, it still works. But, no, okay, this works, that one does not. Take a look at the choice of numbers. Think about how how processing works, and what is the value of 1337 to the power of 1 billion.
Number too large.
Yep, number is way too large. It will not even finish. Yep, so how ABM has optimizations to run much faster. And GTA 6 will probably release before the first one finishes running. Okay, so wait, can we do it then?
Yeah. So like it's not a matter of why can't we, but not it's more so like why do we not do it. So like let's say if A is 2 and then like B is 4 for example and M is like 7, there's nothing stopping us from just doing 2 to the power of 4 mod 7 because we can do it. In this case it runs quite like fast. But the reason why we don't do it is because like if our exponent is very big, for example, and we do everything mod 7, what this will do is that it will first get the full to the power of this, then it will modulo it with 7, which is very inefficient, and this will take forever because I am essentially consuming 121312 whatever that number is, that amount of bits in his RAM I'm currently using to calculate this. So if I leave this running, his RAM will probably explode, so I'm just going to interrupt this very quickly. So we don't want it to actually store the whole number and then mod after. We actually want it to be constantly doing the modulo as it's running the program. So if we do say like power this, we see that it runs very fast. It runs this very quickly because when it's doing power to the power this, every time it goes past 7, it will automatically like modulo it back. Think of it as it doing that way. It's actually not necessarily doing that. It's more so there's a way to optimize this such that instead of running this in O exponent time, so instead of running a loop that exponents it every single time, it actually runs it in O log base 2 of this. But we won't cover this optimization, but it's something that you guys can Google if you're interested. But TLDR is that when you're doing exponentiation, don't do the to the power of that way, just use the power function. It's much more faster and it uses less memory, so it won't crash your computer. Yeah.
Yeah, RAM is very expensive now. So next slide. So now that we have finished the content for modular arithmetic, it's time for math questions, which is what we asked you all to bring pen and paper for. So I have to get everyone to take out your pen and paper, and let's do this question. I'll give you all about 10 minutes to do this question.
For the record, for those for you guys in the Discord, I've sent a bunch of code that is basically about like how to implement GCD, XGCD, as well as other like modular arithmetic functions that we will talk about later. They're in the Discord in Crypto General, so if you want to do any like coding in Python, for example, you want to call like GCD or 1001.871 for example, you can reference the code in Crypto General for it. It's the latest message. Yeah.
And also here's a hint, because this just throwing a question like that is also kind of hard to understand. A hint would be related back to what we covered on XGCD. And feel free to collaborate also. So we'll give you 10 minutes, we'll be back at 36. Okay, so let's go back to our hint, which is XGCD, right? And we remember that XGCD finds some values of XA plus YB is equals to GCD of X and Y, right? And can we go back to the question? We see that over here we have X and Y that we know, and we also have on the right hand side we have it's not our GCD, but if we take the GCD of 1001 and 871, we get 13, which is 26 divided by 2. So let's keep this in mind, but we can kind of infer that we want to solve for the difference. So we can call X GCD on 1001 and 871, which gives us negative 20 times 1001 plus 23 times 871 is equals to 13. So now we have gotten a solution for 13, but we want 26. What do? Times 2. Yeah, that is correct. So we multiply the entire equation throughout by 13. So we get negative 40 times 1001 plus 46 times 871 is equals to 26. And these two numbers are our answers. But they are not the only solutions. As Bizarre's identity says, there exists numbers, which does not guarantee the solution 1. So I'll just give a quick example of one that works, which will be negative 40 plus 871 and 46 plus 1001. Wait, no, sorry, 46 minus 1001. This also works. Anyone want to take a wild guess why this works? Or take a guess, an educated guess. Try and expand the equation. Yeah, but if we do that, that also works. Alright, no worries. I'll walk through it. So, we know that we have negative 40 times 1001 plus 46 times 871 is equals to 26. And if we expand that equation here, negative 40 plus 871 times 1001 plus 46 minus 1001 times 871 is equals to negative 40 times 1001 plus 871 times 1001 plus 46 times 871 minus 1001 times 871. Everyone following so far? So we see that after we expand our equations, we get this monstrosity of an expression. But we see that we have 871 times 1001, negative 871 times 1001. So, yeah, they cancel each other out. And we get negative 40 times 1001 plus 46 times 871. And this is just 26. So, everyone following? Everyone gets why this monstrosity of the equation gives us 26? Alright, nice. So, basically, we have an infinite number of solutions. So now we'll move on to question 2, which says a to the power of p is congruent to 10 modulo p. Find a. We briefly went through this just now, but my hint for this question, or the concept, would be Fermat's little theorem.
Just to clarify, p is prime.
Yep.
Yeah.
We'll give you about 10 minutes for this question. Okay, so now we're going to be going through this question. So let's go back to our concept, which is Fermat's little theorem, which tells us that a to the power of p minus 1 is congruent to 1 modulo p for any a at any prime. Right. So our intuition is that we want to get a to the power of p. So what we can do is we can multiply by a on both sides. So let's do a to the power of p minus 1 times a is congruent to 1 times a modulo p. So what's the left hand side going to simplify to?
A to the power of p.
Yeah, a to the power of p. And our right hand side is obviously a. And if we look back at our question, it tells us what a to the power of p is, which is 10. So a is congruent to 10 modulo p. Yep. Make sense? So since a is congruent to 10, we have a is equal to 10 plus kp for any integer k. Everyone following? Okay, great. So now we're moving on to question 3, which is the hardest question. So I'm not going to read it out, but the concept for this question is not what we have taught, but rather it is expand the expression. So like if it's x squared, you do p plus q squared equals p squared plus 2p plus q squared.
If you don't know the binomial theorem is okay, you can Google it and apply it. Yeah.
The harder version requires binomial theorem. The easier one doesn't. But we'll give you about 15 minutes for this question because it's the hardest one out of the three. And no worries, if you need help, feel free to raise your hand.
So we have n equals to p times q, and we know that p plus q to the power 5 is 67 mod n. So if you were to expand this out, we actually get this really like big equation. So we have like p5 plus 5p4q plus 10p q squared plus 10 p squared q4 q3 plus 5p q4 plus q5. And recall that we know that p plus q to the power 5 modulo n is 67, where n is p times q. So what happens when we mod n? So let's say we do like 11 mod 3, right? We know that 11 is, for instance, in here it's like 3 times 3 plus 2, right? And then because we are doing mod 3, anything that has a multiple of 3, we just cancel and set it to 0. So we're going to do something similar with this. So in here, if we look at mod n, which is pq, anything in here that has pq, we can cancel and set it to 0. So we see that here, right, 5p4q, pq is inside, right? So we can actually just cancel out and it becomes 0. In the same way, p cubed q squared, pq is a factor, so we can cancel it out. And the same way we cancel out this and this. So when we do p plus q to the power 5 modulo pq, we actually get p5 plus q5 modulo n. And because we know this is 67, and we also know that p5 is 76, we have 76 plus q5 is 67 mod n. So q5 is 67 minus 76, which gives us minus 9 mod n. So the correct answer is not just minus 9, but it's like q5 is just minus 9 plus k times n.